Good morning, students. Myself, Vaidegi, working as Assistant Professor in Sri Muthukumaran Institute of Technology. Today, the video lecture is from the subject CEC 334 Analog IC Design. Today, we will discuss about the stability and frequency compensation from the Unit 4. These concepts are extremely important in amplifier and control system design. We will learn how poles affect stability and understand phase margin and study techniques used to prevent oscillations in electronic circuits. The learning objectives are: at the end of this lecture, you should be able to analyze the stability of a system, identify multipole systems, calculate phase margin from frequency response plots, and explain how frequency compensation improves amplifier performance. First, we see about the introduction to the stability. Stability is one of the most important characteristics of any electronic system. A stable system produces a predictable output and settles to a final value after disturbances. If a system becomes unstable, oscillations may grow indefinitely and damage the circuit. Therefore, stability analysis is essential before implementing any feedback system. Next, we see about the poles and stability. The stability of a system is determined by the location of its poles and in the S-plane. If all poles lie in the left half of the complex plane, the system is stable. If any pole lies in the right half plane, the output grows exponentially and the system becomes unstable. Pole analysis provides a quick method to predict system behavior. Next, we see about the multipole system. Real amplifiers and control systems rarely have only one pole. Most practical systems contain multipoles due to the presence of capacitors, transistors, and parasitic effects. These systems are called multipole systems. As the number of poles increases, the complexity of frequency response and stability analysis also increases. Next, we see about the frequency response of multipole system. Each pole contributes a decrease of 20 decibels per decade in gain and introduces up to 90 degrees of phase lag. Therefore, a two-pole system contributes approximately 180 degrees of phase shift, while a three-pole system contributes 270 degrees. This accumulated phase lag can lead to instability. Gain margin and the phase margin. Gain margin and phase margin are important measures of stability obtained from both plots. Gain margin tells us how much gain can increase before instability occurs. Phase margin indicates how close the system is to oscillation. Larger margins generally imply greater stability. Next, we see about the phase margin. Phase margin is measured at the gain crossover frequency, where the gain becomes unity or 0 dB. It represents the additional phase lag required to bring the system to the verge of instability. Designers typically aim for a phase margin between 45 and 60 degrees to achieve a good balance between stability and the speed. The importance of phase margin is very small. If phase margin is very small, the system exhibits overshoot and ringing. If it becomes negative, the system oscillates. A larger phase margin improves stability but may slow down the system response. Therefore, engineers choose an optimum phase margin based on design requirements. Next, we see about the frequency compensation. Frequency compensation is a technique used to improve stability by modifying the frequency response of an amplifier. The objective is to reduce excessive phase lag and increase phase margin. Compensation ensures that feedback amplifiers operate reliably without unwanted oscillations. Next, we see about the compensation techniques. Several compensation techniques are used in practical circuits. Dominant pole compensation introduces a low frequency pole to control the response. Pole splitting separates pole frequencies to reduce interaction. Miller compensation uses a capacitor to create a dominant pole and is widely used in Operational amplifiers. Next we see about the frequency compensation in operational amplifiers. Operational amplifiers often use Miller compensation because it is simple and effective. A capacitor connected between amplifier stages creates a dominant pole and improving phase margin and stability. Although bandwidth decreases slightly, the amplifier becomes much more reliable. Finally, we came to the summary of this lecture. Let us summarize today's lecture. We learned that system stability depends on pole locations. Multipole systems introduce additional phase lag that may cause instability. Phase margin is an additional indicator of stability. Frequency compensation techniques such as dominant pole compensation and Miller compensation are widely used to improve amplifier performance and prevent oscillations. Hope you all understood the concept. We will see in the next video. Thank you.